Okay, just wanted to begin our final session. I'm Joe Nielsen, and I've had the pleasure of working with John Castor for more than 30 years, so he's just been an invaluable colleague all these years. So the first speaker in this last session is Stephanie Hansen. She's a distinguished member of the technical staff in ICF design at Sandia National Labs, where she's an expert in atomic spectroscopic equation of state and transport models, and is involved with many of the HED experiments. I actually knew her since she was a grad student at UNR, and then she came to Lawrence Livermore Lab for a number of years before she left us to go to Sandia. But she's a close colleague of ours for many years. So welcome, Stephanie.
Get my microphone on. Is this transmitting? Good, yes. Thanks. So distinguished does not mean the same thing at Sandia as it does at Livermore. So not that distinguished. And this talk title is a little bit awful, but so I'll go straight into the talk. And the talk you'll hear is combining two threads. One that's kind of a technical thread about making the information of atomic scale models that goes into radiation hydrodynamic models consistent among itself, so you don't get conflicts when you talk about the z-bar that you use in the the equation of state versus the one you use for opacity or for transport coefficients. Because consistency is like the 0th order requirement of accuracy. If you're not consistent, you're not accurate. If you are consistent, you might not be accurate, but at least you're consistent. And I'll talk along the way about how John helped me work through some of the issues that I faced when I was working on all three of these things. The second thread of the talk is more fun, and it is acknowledging the contributions of John and others at the laboratory in the help that they give to young scientists who are coming in and learning how to do these things. And so it was a delight to work at this laboratory, because you can find a paper written before you were born and go, what the heck does that mean? And walk down the hall and talk to the author of the paper or the book and say, what the heck does that mean? And the fun thing about Livermore, I mean, you look at the nightly news, right, and you see that the combination of brilliance and kindness is in short supply in the world. But in the laboratory, it's not. And so people like John and Brian and Carlos and Phil and so many people here are both brilliant and kind, and that's, I think, why we make the progress that we do. So when I got to Livermore, Paul Springer and Steve Libby were interested in getting non-LTE into hydrocodes. And I thought, well, I know non-LTE physics, but I know nothing about hydrocodes. And so I'll buy John's book, and I'll try to follow the instructions and write a hydrocode, and I did. It was terrible. Didn't work very well. It got the set-up blast tube, and it got the Marshak wave, and it was so clear and direct, as the review of the book says, that you could code up a 1D hydrocode in about a week, thanks to John's book. When I tried, and I don't know if it was my implementation, I'm certain it was, but when you tried to go to more complex things, it didn't work quite as well, so I decided to focus on the atomic scale. And when you look at things really closely, you see quantum mechanics, and so this is kind of what this talk is about. The model that I'll be talking about, again, trying to make all these constitutive properties that you use in radiation hydrocodes consistent at least, is based on a fully quantum mechanical picture of all electrons and a classical picture of the ions. And so the electrons, looking as a function of radius, have some structure that represents electronic orbitals in materials. This example is iron, and so you see the 1s and the 2s and p, and the 3s, 3p, and 3d. There's a 3d orbital here. I'll talk more about it because I love it. And then if you just treated the electrons as a fluid, you'd get something much more smooth, like that gray curve, the Thomas-Fermi curve. So in this model, you guess a potential, you find the wave functions, you populate them according to Fermi-Dirac statistics. That gives you a density from which you can back out another potential, and you iterate this process until the potential and the electron density are consistent. This is kind of the basis of the model Purgatorio, which feeds into a lot of the EOS models used here, except instead of a muffin tin, where the potential goes to 0 at the Wigner-Seitz radius, this model feels the effect of other nearby ions with some kind of radial distribution, G of R. And so this comes, I have to thank Brian Wilson and Vijay Sana, Charlie Starrett, and Balazs Rajniak, because they helped me implement this kind of model more than I can say. I pretty much just copy their work. Except for one thing, and that is to ensure smooth transitions. When you squish these electrons close together, you can get what's called a resonance feature, so the 3D orbital can develop a wave structure and extend throughout the material. And if you try to extract the bound state character of that orbital, then you can make an ansatz about the ionization state of the material that guarantees smooth transitions under this process of pressure ionization. When a bound state moves from a delta function at negative energy, a true eigenvalue of the system, to a distributed peak at positive energy. And this has several advantages that I'll show you. And Brian helped me a lot in doing this. So then if you want to do mixtures, you have to do something complicated, which is almost trivial in the Thomas Fermi picture where the electrons are smooth, but can be a little bit tricky for quantum models, where Z bar is not a well-defined quantity, and you can do either pressure or chemical potential or density matching, and they're not always the same, whereas they are in a Thomas Fermi approach. And John helped a lot with that. John and I had many conversations about mixtures, both for the equation of state and for transport properties, where I just didn't know what to do. And he would sit down and we'd talk for about 10 minutes, and I'd come away with exactly what I needed to know. So, okay, we have this model. It's got electrons, it's got ions. What else can it give us? It turns out quite a lot. So there is a commonly used formula for the transport properties, the electrical conductivity of a plasma, that depends on the wave functions, the electronic wave functions, that feed into a cross-section that tells you how much things scatter and collide as you're trying to move particles through a field in a plasma. But it also has a dependence on the ion term. And since in this model, the ions and the electrons are self-consistent, the same potential that gives you the electronic wave functions gives you the ion-ion coupling that leads to the structure factor, there's much less of a chance of generating compensating errors than there would be if you took a cross-section from one place and a structure factor from another. When I was at Livermore and I worked on transport models, I'd take the OCP structure factor, which is shown here by this dashed line, one component plasma structure factor, and it gives you something that goes to 0 at the 0 reciprocal space. It's the Fourier transform of the G of R, the ion correlation function. But if you solve the quantum Ornstein-Zernicke equations with a self-consistent potential, you get something different. And that can matter. It doesn't matter too much because you've got this k cubed term, but it can matter, and it gives you a thermodynamic quantity, the isothermal compressibility, that you can also get from thermodynamic derivatives, and those things better be consistent. So this is one test of consistency in a model. As you heard in Heather's talk, and I should say that Hugh DeWitt was one of the people whose papers I found and went down and said, Hugh, what do you mean by this in the OCP? And he told me, and he gave me a Fortran code that explained exactly what he had done. So that was a delight. And then when I tried to extend this from electrical to thermal conductivities, I again went to John, and he pointed me to a paper by Hubbard and Lamb, where there's this non-Lorentz reduction factor that comes from the electron-electron collisions. And again, you heard about this from Heather, and Lauren touched on it a little bit, but it gives you an additional source of scattering that reduces the thermal conductivity And it's critical to get agreement with especially light elements like hydrogen with other approaches to calculating those opacities or those conductivities. Another thing you can do with an average atom model like this is generate optical properties. You have the electronic wave functions, so you can compute matrix elements. You can get frequency-dependent conductivities, which, by the way, ought to be consistent with what you got from the Zeeman conductivity formula at zero frequency. You can get frequency-dependent dielectrics. The dielectrics lead into things like stopping powers and other transport properties we heard about from Lauren. And you can get opacities, absorption cross-sections. You may also be able to get lifetimes, and this is speculative. This is something I'm still working on, so don't take it too seriously. But if you get lifetimes and cross-sections, you can get something to inform collisional lifetimes that tells you how lines broaden. So one of the problems in opacity is knowing where the lines are and how strong they are. Another problem in opacity is knowing how broad they are. And they can broaden by either collisional processes, spontaneous processes, thermal processes, or Stark effect. But in fact, we have the ion structure factor, so we can also get the electric field probability distribution and estimate the Stark widths. And I'm not a line shape expert, Carlos is, and I'm working with somebody who is becoming an expert on this. But these would be things, recipes, ingredients in a recipe for a consistent line shape model. And so far, I don't think one exists. So this could be an exciting direction for research. Oh, and by the way, when I asked John about the non-Lorentz reduction factor, I misspelled it with a ZT because I was accustomed to Lorentzian line shapes, and he corrected me kindly and said, no, this is a different Lorentz. Scattering calculations. Here's another really interesting thing. People have been using X-ray Thompson scattering as a diagnostic for warm dense matter. And so you throw in an X-ray photon and it scatters from free electrons, undergoes a Compton shift, gives you a downshifted peak from the original X-ray energy. It can also scatter from tightly bound electrons, not undergoing the Compton shift, and give you an elastic feature. It can also scatter from bound electrons and help them undergo a transition, giving you a bound-free feature. And some work that I did trying, again, to make this picture of scattering look consistent from, as you make a small change in density, going from 5 grams per cc to 8 grams per cc, the scattering signal shouldn't change very much. But in traditional scattering models, because you're going from a z-bar of about 3 to a z-bar where 3D is ionized, so you go to z-bar where 8, you get a profound change in the free scattering. But if you do it quantum mechanically in a consistent way, and here I'm following Charlie Starrett, you get a much more consistent picture under compression. And then you find that you have to also include bound-bound transitions. Now, this doesn't really matter for low Z elements, where this has most often been used, but it matters a lot for high Z elements, and you better have this term, or you won't get this nice, smooth transition as you pressure ionize an orbital. So I saw this and I thought, well, that's fantastic, but is it true? There are no experiments with the resolution to see this. So the next best thing to an experiment is a high-quality calculation that takes a couple of weeks to run. And in this case, that was time-dependent density functional theory by my colleague Andrew Bashewski. And he showed, the blue line here, that indeed there do appear to be bound-bound scattering features in the scattering signal. So I thought I'd take a drink of water while you looked at these horrible equations. And I didn't put them up there to talk about them. I put them up there to say, oh, it's hard. And when things are hard, it's tempting to simplify wherever we can. And often that works. It often works in the limits of a classical plasma. It works in condensed matter. But when you get to really extreme states of matter, it stops working really well. And you need to know when it's okay to simplify and when it's not. Because if you simplify by taking different parts from different theories and smashing them together, you get something that looks like Frankenstein and goes, and then kicks your laser down, or whatever. So the idea here is that if these moving parts all come from the same model, then they'll interact smoothly, and you won't get compensating errors. So another person at Livermore, Andrew Ng, ran the Jupiter Laser Facility while I was here, and he made a measurement of the optical conductivity of gold. And I said, well, I'm calculating conductivities, I'll calculate that. And it agreed very well. But Andrew went further. He measured the lifetime and the charge carrier density. And those two things multiply together to give you the conductivity. And the lifetime that I had was an order of magnitude too low, and my charge carrier density was an order of magnitude too high, but I was getting the right answer. It was for the wrong reasons. And so this I took as a serious lesson. You've got to, you risk being right for the wrong reasons if you don't take care in making the parts of your model consistent. And again, this model might not be right, it might be wrong, but it's going to be consistently wrong. And like Heather said, when you fail in a spectacular way, so everybody knows you failed, that's actually a good thing, because then you're not fooling yourself or anybody else. So consistency matters, completeness also matters. That means if you're doing a calculation, you better have all the parts, and they better all be consistent with each other. And completeness is hard. Completeness is difficult, especially in opacity models, where you have to include transitions among, the scale goes from 1 to 10 to the 22, among states that can have statistical weights for complex ions of 10 to the 16 or 10 to the 20. And that's only if you're doing double excitations, but you actually need multiple excitations. So solving this in LTE, much less non-LTE, is a real challenge. Now, I showed you can get opacities from the average atom type model, and they take about a minute to generate an opacity. And it's a crummy opacity, right? It's got the lines in the wrong places. It doesn't have enough lines. But in the continuum, it's actually not bad. And it's not bad because it's complete. The completeness is intrinsic to the model. You can work really hard with other models and enforce the completeness, count all these states, and get something that looks more like the experiment, which is here shown in black. This is Jim Bailey's experiment. And then you can work even harder and include configuration, interaction, and other fine structure effects and get something that looks even more like the experiment in where the peaks are, if you enforce the completeness. But it doesn't look like the experiment in terms of the absolute value of the opacity, and this is one of the outstanding problems in our field today. Why? What's missing? We know these models are complete, and we know they're complete because they agree with the average atom. So in this way, it's a useful check on the consistency of these more complex models. And it's an essential check because when you do even harder work, so this takes about a minute, the average atom, the UTA takes 10 minutes, the hybrid model takes 100 minutes, something like that. There's a group in Ohio State that's working really, really, really hard to get everything exactly right, and they're using a model called close coupling, where it takes a month or a year to get just one ion stage, not even the whole atom. And they're really happy about how accurately they're getting the lines, which Carlos will caveat for you if you wish later. But they didn't check the basic zeroth order requirement of completeness. So they were coming in lower than most other opacity models that know and acknowledge this requirement. So this is still an outstanding puzzle. The issue that I first came to Livermore and started to pursue, this issue of radiation of non-LTE in rad hydro models, has now been more or less solved by Howard Scott, and I just learned over the break was solved also by John Castor. In yet more work that was unacknowledged. This has been so fun to see all the things that he's done that I didn't know about when I was already super impressed by the stuff I did. So here's a speculation. I told you you can get absorption cross-sections and maybe lifetimes from an average atom model. Well, one way to resolve the opacity problem that's being investigated by Richard Moore is two-photon absorption. And Richard Moore is doing a really good job calculating this. This is an example of a bad job calculating it, but it's fast, and so I like it. If you have a picture of a two-photon absorption process, of a photon being absorbed in one state into some transitional state, which may or may not be a real state, it may be a virtual state, and then absorb another photon before it has time to decay, then you can picture it as a sequential process that's a product of two opacities and some lifetime. And the lifetime of a bound state you can estimate by calculating collisional and radiative decays. But what is the lifetime of a state here? If you don't, what is the lifetime of these virtual states? So just multiplying, taking this product and integrating over the black body of the backlighter, you can get one photon opacity in black for the two conditions that Jim did his experiments, one of which agreed with standard models and one of which didn't. And then the two photon opacity integrated over the black body, that is very speculative, as at the two conditions. And it goes in the right direction. It's a larger contribution for the case that didn't agree with standard models than for the case that did. I'm not sure that this is even the right approach, that there's any way to get a two-photon opacity from an average atom model, but I think it's worth pursuing. This is kind of a fun result, too, in the last one that I'll show. When you push material to ever more extreme conditions, like we do at NIF and on platforms like Z, where we compress material in order to inertially confine a fusion plasma, we get material that has different screening than anything we see in the stuff that we're standing on or the stuff that we eat or the air that we breathe. And this is reflected in the emission lines of that material. So spectroscopy can help you understand what's happening on the atomic scale of material at extreme conditions. So Brian Wilson, a long time ago, sent me a table of binding energies for all ions of all atoms from the Limbo code. And if you look at those results, you see that the fluorescence lines, that's the 1 to 2 transitions from near neutrals as you ionize the 3D electron. The 1 to 2s will shift slightly to the red, they'll go down in energy, and the 3 to 1s will increase in energy monotonically as you remove electrons. We did this experiment where we compressed fusion fuel. It lit up. It caused fluorescence emission in the impurities of the beryllium shell. And we saw a small redshift in K alpha, the 2 to 1 transition, which was not unexpected. And we saw a huge redshift in K beta, which was unexpected. And it was beautiful, because what it meant that instead of removing these electrons, you were adding electrons. You were changing the screening so that you got a redshift. We also saw absorption of the K edge of the iron impurities in the beryllium, and can use it to help distinguish between different ionization potential depression models. And this is almost embarrassingly good agreement, but the experiments are here. The average atom calculations are here for the K beta shift, the K alpha shift, and the edge shift, which doesn't shift much at all. And the predictions of various IPD models are here and here and here. And so in agreement with some previous work, Stewart Pyatt, a standard model, probably doesn't give you enough IPD, but some other candidate models do even more poorly. So to conclude, got models, and they're hard. But the more you can make them consistent, and the more you can make predictions of observables from those models that are consistent within the framework of those models, the more confidence you can have in your plasma diagnostics and in the radiation hydro results that you use to design and interpret experiments. And so these include scattering and collisionality in transport, as well as equation of state. And it is a virtue that if the present model is wrong, it's consistently wrong. And it's not fortuitously correct, or it's not correct because you tuned it to be so. And you can determine that wrongness or rightness, maybe, by measuring any one of interdependent observables. But the more fun part of this talk is that the environment, the collaborative scientific environment that exists here and at, I think maybe even to a bit lesser extent at some of the other national laboratories, because of just the massive brilliance and kindness that is here at Livermore, offers researchers amazing opportunities, especially young researchers, to develop and apply their own scientific contributions. And so, thanks, John.
Time for some questions? Yes, John.
Can you go back to the slide with the ionization depression? Yeah. Okay, that looks pretty bad for the simplified models there.
Yes, it does.
Is there something we can conclude about regimes in which it's bad? For example, is this at a particularly extreme coupling parameter?
Yeah, that's a good point. This is in fully degenerate material, and so the temperature is about 10 eV. You can tell by how that edge is shaped.
Yep.
And the density is about 10 to the 24. So the Fermi energy is 50 eV. And in the other measurements that have been made were made in different regimes. So Dave Horty's experiment at Orion, which also confirmed the ion sphere model of IPD, was made at higher temperatures and similar densities, but not degenerate. And then the original work that invalidated Stuart Pyatt, which does seem to be invalid, was done at higher temperatures and higher densities. So it was on that border between degeneracy. So it seems to me, but I'm biased, so don't take this to heart, that the ion sphere model does pretty well everywhere. Any self-consistent DFT model will do pretty well anywhere. These simpler models will fail differently in different places, but they'll fail subtly, not spectacularly.
Other questions? Well, let me ask a question. So what experiments should we do to give you more confidence and
Oh, gosh.
to measure these shifts?
Put a buried layer of some transition metal on NIF and then backlight it with the plasma and make sure it's degenerate so you can use that edge to tell you where the IPD is.
Okay, this is very exciting. And,
Oh, and then also scatter X-rays from it. And measure it with a high-resolution spectrometer that has also time and space resolution and a spectral resolution of that.
right. I will bring that to Peter Biesdorfer's attention since we have this super high-res spectrometer he's developed, which could be perfect. If
Yes,
was
it
at
could.
The,
Yeah, OREX would be great.
yeah, OREX would be great for this. Okay, well, let us thank, John had one more question.
On the two-photon. So maybe what we need is a systematic campaign of calculating the two-photon correction to the opacity.
Yes. We need calculations, and we also need to understand how those what they imply for the experiments that are going to happen on NIF. So what these calculations, which I'm not claiming are correct, imply is that you will not see a difference between experiment and theory when you make that measurement. That theory will lie right on the experiment will be low, it will be lower than the cold opacity because the backlighter is far away. So the determining factor in that theory is the photon flux from the backlighter. And so Michael Cruz, I know, is looking into this computationally here. Richard Moore is doing work, but yeah, I totally agree.
Right, and you certainly want to be complete.
Yes.
You don't just add enough to get
Don't
the right
just do
answer.
one line.
Yeah, right.
That's right, and then stop.
Yeah, and then stop.
So Stephanie, does that mean, the sun doesn't have a backlighter, right? So does that mean that This is a fluorescence problem. It's a non-LTE problem.
It might be a non-LTE problem in the sun, but if you remember, the astrophysicists were really happy by Jim's result because they needed a higher opacity to match helioseismic data. And so, but if this is happening, it's something we all need to think about pretty hard.
Okay, well, let's thank Stephanie again.